Good afternoon, everybody. Welcome, and nope, I got pinned myself right. Welcome to another fun afternoon of organic chemistry, Chem 170, with your host, me, Dr. White. Now, if you look at the syllabus, next Wednesday will be test 3. And I thought it might be better to do it on Monday instead of, I might have said today, but on Monday, I will go through the amines, amides, and quaternary ammonium salt problem set. On Monday, I will give my world famous review for the next test, in this case, test number 3. Also, we'll go through new material. And I didn't have a chance to post it yesterday, bad Dr. White. I got swamped with a lot of personal stuff. But anyways, by, let's say Wednesday, by Friday morning, I will have posted the points breakdown for test number 3. I can tell you it's going to be similar as it was for test number 2, about 35 points, 35 points nomenclature. Nomenclature questions are 2 types. Here's the structure, give the IUPAC name, but this one's going to be different. Since I didn't teach you IUPAC name for amines, the nomenclature question will be, here's the structure, give the IUPAC or the common name. And the other one will be, here is the name, draw the structure, which for amines can be both common. Well, I didn't teach you IUPAC for esters and others, IUPAC. Now, there'll be about 60 points for reactions, at least 3 will be 3 or 4. I don't remember how many. I just finished writing it over the weekend. Will be synthesis. Here's the product. What is the starting material? And I think about 10 real world problems. Hi, Tam. And it'll add up to 105, which means there's going to be 5 bonus points. So I'll post that by Friday at the latest, the test number 3 points breakdown, which will be a week from today. We'll take it the same way you've done the others. At the end of the lecture lab period, next Wednesday, I'll send out an email with the password, and you'll have until 10 or 11 o'clock the next morning to take test number 3 and upload your answers as a single PDF file. Any questions? All right. By the way, I didn't have time yesterday. I'll do it today or tomorrow. The labs you handed in last week, I've graded, and I'll post those into D2L. Like I said, either sometime tomorrow, probably. And don't forget to hand in the lab that's due today. All right. Now, like I said, on Monday, I'll do the problem set for amines, amides, quaternary ammonium salts. So let's get back to fats and oils. Now, on Monday, I talked about saturated fats, fatty acids, and those are molecules that are carboxylic acids that come from the acid hydrolysis of fats and oils. And turns out Mother Nature always does even number molecules or fatty acids. There's no odd number and there's no branching either. And the one saturated, and saturated means, and here this means fatty acid, is a carbon chain with which all carbon-carbon bonds are single bonds. Do not put down all bonds because you've got a carbon-oxygen bond, carbonyl, which is not a single bond. And I asked you to learn one specific saturated fatty acid. And that's this, and this is stearic acid. And remember to bracket something inside, close bracket, and then a number subscript tells you, ooh, I just made a mistake. Glad I caught it. Is how many CH2s connected? It'll be CH3, CH2, CH2, and so on, where there's 16 of those. It's easier to draw it this way, so you'll never see me do it that way for this, and that's stearic acid. And you should know the structure. And I went through oleic acid, which is a mono means one, unsaturated for fats and oils in Mother Nature. She never did a triple bond. So unsaturated means at least one carbon-carbon double bond is present in the R group, or in this case, one is because it's monounsaturated. And I asked you to learn the structure of oleic acid, which is this. And remember, the carbonyl carbon is one, so plus 7 S8, that means this carbon is C9, and that's where the double bond is. Now that can be cis or trans. Remember cis. The double bond, the hydrogens are on one side. And the hydrogens on the double bond, and the squiggly line is the rest of this stuff on either way, is on opposite side, and that's trans. So that double bond can be either cis or trans or a mixture. Now, I won't ask you to learn this, but there are also polyunsaturated fatty acids, and poly means many, more than one. And these can have two or more. And one of them is called linoleic and the other linolenic, which I'm not going to ask you to learn. One has two double bonds, the other three. Now, switch is on for this one. This one, the switch was off for polyunsaturated. Now, fatty acids can have cis or trans, as I showed you previously. Now, that makes an important thing. If you think about it, and say hello to your roommate, tell him to leave your hat alone. But anyways, when you have a double bond, I'm going to get to this later. There's a better place I can talk about. So your fatty acids can have cis or trans double bonds. All right, now I'm going to go over some stuff that's really not well covered in the book if you're reading the book, and there are a few things you should learn from this. Now, there are different types of fats and oils, and the first one you should know is beef fat, which is not called that in the chemical industry. You should know that's called tallow. And tallow is abbreviated sometimes BFT, which stands for bleachable fancy tallow. That's the highest grade. But tallow is beef fat, and you should know beef fat is called tallow. Now, another important fat and oil comes from pig's fat. If you've ever made bacon, it's left behind in the pan after you fried up your bacon, it's called pig's fat. But in the cooking, they call it lard. But you should know that yellow grease and white grease are pig's fat. And the difference is how light a color they are. White grease is a penny more too expensive to yellow grease. If you're buying 100 million pounds a year, that makes a big difference. But those are pig's fat. Now, I work for a company, Unichem Chemical, located not far from the old Comiskey Park, in what used to be the Stockyard area of Chicagoland, or Chicago, the city proper. And we purchased tallow, white grease, and yellow grease to the tune of 2 to 3 million pounds a week. Yep, 2 to 3 million pounds. Now, whenever our buyer could get white or yellow grease, we would, because it was always less expensive than tallow. Now, you might want to ask, how important is this stuff? Well, many contracts for a lot of chemicals that you use that are made from these compounds, their price is based on the weekly price of these commodities. And where can you find this? I bet you'll be surprised. The Wall Street Journal. If you know where to look, once a week on Friday, they have the price per pound. I forgot FOB, what city. FOB is freight on board. But anyways, tallow and yellow grease and white grease. Now, other oils, coconut oil, soybean oil, you might be familiar with. Corn oil, you might be. A mixture of these are called vegetable oil. Olive oil, which in the last decade or so has been very popular because people are saying how healthy it is. And then there's one called rapeseed oil. Anybody out there ever hear of rapeseed oil? Nope. Guess what? Rapeseed oil is probably one of the widest used cooking oils in the world. It's quite inexpensive. It comes from a plant that's called the rapeseed, or this rape plant, and they have the rapeseed from it. Now, one place that grows a lot of rapeseed for rape, makes a lot of rapeseed oil, is Canada. And when they tried selling rapeseed oil in the United States, housewives wouldn't buy it. Hold on. 3 more rings. Sorry about that. 2 more rings. 1 more ring. It should stop after this one. There it is. My answering machine picked it up now. All right, sorry about that. Well, anyways, the housewives wouldn't buy rapeseed oil in the United States. Well, this is made in Canada, and somebody at the collective or the farmers group for rapeseed oil came up with a great marketing idea. Well, if they won't buy rapeseed oil and it's oil made in Canada, why don't we call it canola oil? How many of you have heard of canola oil? Everywhere in the world, it's called rapeseed oil, but in the US, it's called canola oil. And once they changed the name, because it was less expensive than other oils, housewives started buying it. Isn't that amazing? But you should know beef fat, tallow, pig's fat, yellow grease, white grease. Now, if you think about it, the fatty acids come from the acid hydrolysis of different fats and oils. And you don't have to know this chart, but I thought I'd just show it to you. If you look at the different types of fatty acids, you can have 12 carbon stearic. These are common names. Palmitic is widely used. Stearic are the main ones, and unsaturated oleic. And as you can see, linoleic, linolenic. And now here they have cis and cis. Whoever wrote this chart was wrong, because they can also be trans. Oleic is not all cis. Trust me, I know quite well. Now, when you look, and the switch is off for this slide, if you look at their 2 types of fatty acids, and they come from the oils or fats, and that tells you the R groups on the ester of the fats. And if you notice, for animal fats, butter, lard, which really is yellow grease, and here, see where someone said beef tallow? the person who wrote this chart didn't know the chemical industry of fats and oils, because you can't have any other kind of tallow. It is beef. And human fat, notice they're about 50-50, maybe a little more, unsaturated to saturated fats. But if you look at the vegetable oils, which are liquid at room temperature, where these are solid or semi-solid, you have a lot less of the saturated and more of the unsaturated. If you notice olive oil, combine these two numbers, almost 90%, and corn oil, 80, peanut oil, 85. And the more unsaturation, it's going to be a liquid at room temperature, more liquid. And medical science has said unsaturated fats, which produce unsaturated fatty acids, is healthier for you, healthier, not absolute, healthier than saturated fatty acids, which are coming from saturated fats and oils, or those that are high in saturated fatty acids, meaning the R group. I thought I'd point that out. All right, now, since I've worked in this industry and know it well, how did I know it well? Well, I was laboratory manager for Unichem Chemical all of North America, which meant this was a major international company. And for all United States, Canada, I was responsible for research and development and also quality control at their big plant here in Chicago. So I got to know the industry quite well. And I figured when I first started teaching this chapter, how can I make this more real world? And I came up with a good idea. So let me share that good idea that you should know. If we think about a fat or oil, a triglyceride, has this structure. So how do I make it real world? Well, the most widely used fats in the chemical industry and oil, mainly fats, are yellow grease, white grease, and tallow. And they have a very similar composition of what are R prime and R double prime. And they're roughly 50% saturated and 50% unsaturated. So I decided, well, let's make it easier, because how do you take three things and do 50% of each? Well, you can't. So I came up with the following that you should know. And whenever I say tallow or yellow grease or white grease, I'm talking about the structure, and you should know that. Now, what's R sub O and R sub S? By the way, this is also a little joke of mine. Look what this spells out, the subscripts. SOS, save our ship. But anyways, let's look at stearic acid. And one way of abbreviating stearic acid, on a test, if I asked you to draw the structure, show the carbons, but In this structure right here, using R sub S, what that really means is this. And the R sub S is this part of the sterol. And similarly for our oleic, excuse me, I think I stifled a sneeze. Have you ever had one of those slow developing sneezes and you stop it? I just did it. All right, oleic acid is this structure, but you can abbreviate it like this. And this we'll call R sub O. So what this means is, here's a fat or oil, triglyceride, made up of oleal and steryl R groups. And when you hydrolyze this with acid and water, you'll get stearic and oleic acid and glycerin. And this is something that will help you understand the real world. So everybody have this down. R sub S means this group. R sub O means this. So let's look at something. The following you should know. And I could have also put down here HCl, which is an acid. And the question is, give the organic product or products for that. Well, how do you do that? How do I react out? Well, you remember, this is the structure you should use for that whenever you see tallow, yellow grease, or white grease. So I can now say what it really means is this. And remember, I promised the other day, no new reactions. So remember, the general reaction is, and fat, when you're writing a fat or oil, we write it backwards. Oil chemists do that. So if we look at this one, we have 3 esters. The first ester gives me this alcohol. And now notice R prime is R sub S, so we'll get stearic acid, which, unless I'm asking you for the structure, you can abbreviate that way. The second ester, this is the alcohol I'll get. And now my R sub prime is R sub O, meaning you get oleic acid. Oops. And finally, the third ester, this is the alcohol I get. And you get, if you notice all together, that's glycerin. And we get R sub S again. Now, you could, if you wanted to, put a 2 there. But on my problems, it says, give the organic product or products. And you get glycerin, stearic acid, and oleic acid. So that's your 1, 2, 3 products you get here. And that's how you do it. Now, do I have time? Oh, I do. Now, where I worked, and if I had said instead of tallow, white grease or yellow grease, it would be the same thing. And where I worked, we interchanged all three. Now, interesting thing, you make some good money selling fatty acids like stearic and oleic, which we did. And you can also sell the glycerin at a good price. Sometimes, depending on the market, you make more from the glycerin than the fatty acids, or other times it's the other way around. Well, one day, the president of the company of the United States called me into his office and said, I was just thinking we could make a lot more money from glycerin if it was kosher certified glycerin. If you're not sure what kosher certified is, that's the dietary laws, the Jewish dietary laws, which are similar to the Muslim halal laws. I don't know about exactly, I'm Jewish, I know them. And I told them, well, do you want to spend about $80, $100 million to do that? And he looked at me like, what? I said, we buy yellow grease and white grease. That's pig's fat. And one of the first things in being kosher is you can't have anything made from a pig. And I don't keep kosher myself, but I have relatives who keep kosher. And I know that from my childhood too. And I said, either you got to stop buying yellow grease and white grease, or you build a new plant. And he said, well, I'm not going to stop buying yellow grease and white grease. We may save a lot of money that way. I said, yeah, I know that. But as long as you bring that into the site, unless you build another separate plant right next door to ours, you can't get kosher. So he said, are you sure? And I said, well, let me check. And this a little, it won't be on a test, but I thought I'd teach you this. Throughout the United States, there are different organizations that certify things kosher. And the largest one is the Union of Orthodox Rabbis. In fact, a cousin of mine for many years until he retired was the president, he was a rabbi of the Chicago Rabbinical Society and dealt with that organization. And let me show you something. All right, everybody see a bunch of different symbols on your screen now? Thank you. Now, if we look over here, let me see if I can pull this. See the circle U? That's the most widely used certification in the United States. Different parts of the United States have, but circle U, Union of Orthodox Rabbis. If you see that on something, it's kosher. Also, if you see a small K, that's for the Care Ruth, and they have different ones, and there are other organizations too. Now, this one right here, this is the Hebrew letter for the first letter in the Hebrew word kosher, good. And yes, I speak and read Hebrew. And these are different ones. Now, if you wonder, how prevalent is this in our society? Well, it's a secret, unless you know the secret. Can everybody see above my finger the circle U on my label? That means this water from this company is certified kosher, which if you keep kosher, you'll buy that product. And they can charge a little more too. And also a lot of people who don't keep kosher like to buy kosher because it's made to a higher standard. And I called them and I told them what the situation was, talked to an expert who dealt with the chemical industry at the Union of Orthodox Rabbis who certify kosher. And I said, here's the situation. Here's what we do. I told the president this. Was I correct? He said, sure, you can. And then about a month after that, there was an interesting story in the Wall Street Journal. When I was at that company, senior managers got their own copy of the Wall Street Journal every day. I did. And there was a company in China that made different seasonings or flavors. I'm trying to think of the right name for it. But anyway, seasonings, and they wanted to get kosher certified so they could charge more money. It's more valuable. So Union Orthodox rabbis, they paid to fly someone out to inspect the plant, and he did. And he came back to the owners, or it was the state company, I don't know which, I forgot. And he told them, I can't certify you kosher. Why not? Well, go into your lunchroom. Half your workers are eating things with pork. And if you have any pork on the site, guess what? I can't certify you kosher. Well, anyways, guess what? The owner trained his workers not to bring in, I don't know how they did, I forgot. I think they set up a lunchroom in there that they provided food and wouldn't allow anybody bring it on site. And the rabbi came back, inspected and saw, and then they certified it kosher. And they could charge a lot more for their spices and make more money. All right. Now, another important thing about this is if you have something like olive oil, I'm not talking about Popeye's girlfriend. Anybody out there know Popeye? Never mind. I think I just did a semi-generation ago. Olive oil is highly unsaturated, and a good way of representing that is like this. Now, the reason I'm showing you this is, notice here you have the allyl group, which means this right here. Now, that double bond, as I mentioned earlier, can be cis or trans. Now, how many of you have heard of, over the last number of years, medical science has told us that trans fats are bad for us? Have you heard that? What are they talking about? They're talking about this double bond that's in the R sub O. And if it's trans, it's bad for us. If it's cis, it's better for us. And there are ways of converting it, but it costs money. Before, places like McDonald's used to use in their fryers beef fat that was mainly trans. And because of the medical science, more really, because they wanted to keep customers and impress customers, they now use only cis fats. And that's what they mean by cis and trans fats, and you should know that. Now, while I'm here, hold on, let me. What did I do? Hold on. That's what I did. Somehow I accidentally turned on the header. All right, let's get through this. Why don't you try this one? What would be the product or products for the following? Tallow plus sodium hydroxide and water. Now, remember, for tallow, yellow grease, and white grease, you use this structure. Now leave it up in case you haven't copied it down. And you react that now with sodium hydroxide and water. And in case you forgot, I'll help you out one more step. It's Dr. White being nice to his students today. and that will help you out. And when you're done, give me a thumbs up. Oh, by the way, a commercial from Dr. White. If you know anybody who needs organic chemistry, this coming spring, I will be teaching Chem 170, thank you, Megan, online totally. So if they're anywhere in the world and they have internet access and they want to pay to take the course, tell them to register. And I'll do the same thing like I've done now. I'll post videos, but it helps when you come to class in case you have any questions. And when you're done, I know one of you already have, give me a thumbs up. Thank you, Galvin. By the way, private question to Calvin. How many people do you know understand offsides in soccer? I do. Most Americans don't. They have no clue what's going on. But then again, when it comes to what's the English game, wicket, I have no clue what's going on in that game. But soccer, I do. Oh, when I was in high school and we played soccer in gym, I was the defensive back. I played it more like football. If there's someone I didn't like who had the ball, well, I sort of happened to run into them. They didn't give out yellow cards in those days, or I would have had a lot of red cards. All right, everybody done? All right, how do you write tallow? Tallow is this triglyceride. I could have had 2 O and 1 S, but I like my joke SOS, so I use it. And now we're reacting this with sodium hydroxide and water. As I wrote up here, but I'll write again down here, you have an ester, and oil chemists write it backwards. And good habits I don't change. When I'm doing this earlier as a synthetic organic chemist, I write it the other way, but as an oil chemist, I write it this way. So we have 3 esters. Do ester number 1, I'll get this alcohol plus this carboxylate anion of the carboxylic acid I would have used to make that ester. And that's called sodium stearate. Second ester, I'll get this alcohol. Remember, CH is my R group here. And now I have R sub O, so I'll get sodium oleate. And finally, the last one, ester number 3, I'll get this alcohol, but notice this will give me sodium stearate again. So for those who must, you can put a 2 there, but you don't have to, because there are really 3 products: glycerin, sodium stearate, and sodium oleate. And that's what you get. Now, this was the way our ancestors made soap. They boil lye, sodium hydroxide, and water with beef fat. And you make glycerin, which I don't know what they did with back then, but this is in the water a white solid. And you put those 2 together, or they come together. In those days, you did it in a big metal pot, or later vats, and you press together and you make bars of soap. And that's sodium. You do that. Now, Are we doing time-wise? We're doing good. Now, I promised no new reactions. This is sort of a new, but sort of not new reaction. Sort of like maybe, but yeah, it's sort of a new, but not real new. And that's hydrolysis. That's the reaction of a fat or oil with steam. Now, if you've ever worked in a chemical plant, and I have, you have available what's called high pressure steam. High pressure steam has a lot higher boiling point, meaning it's a lot higher than the boiling point of water. I forgot the exact temperature. Let's see if I can find it. Wow. Depending on how high your temperature is, here's some Fahrenheit, just so you know. Water boils at 220 Fahrenheit. High pressure can go up to 1200 degrees F. We didn't have it that high. Let's look at medium. We're about 400 Fahrenheit, which is approximately 200 degrees C, double the boiling point of normal water. Now, why is this important? Now, in chemistry, there's a rule of thumb. It's on this, can you see it's on that thumb, that the reaction rate doubles, goes twice as fast for every 10 degrees C, you raise the reaction temperature. So when you make something go hotter, react hotter, it goes faster. Now, earlier, we've done some reactions where I add a catalyst. And what does a catalyst do? It makes a reaction go faster. So there are two ways you can make a reaction go faster. One is add a catalyst. The other is run it at a much higher temperature. And that's what this does. And let me show you how that works. And then we'll come back after a break and take it for a spin. And steam, remember, is hot water. Now, you learn that if you take acid and water, you'll get an alcohol plus a carboxylic acid from an ester. Well, guess what? Steam does the same thing. Instead of using an acid catalyst, oops. We use hot water, and the heat makes it go fast, so you don't need a catalyst. And guess what? You get the same thing. Now, what's the advantage of doing this one versus this one? Well, acid is dangerous to work with, so is steam, and you have lower costs because one, you just have to heat up the water. The other, you heat it up a little, but you have to go out and buy hydrochloric acid. You've got to store it. You've got all the safety considerations of storing a very dangerous chemical. So you use steam. And the company I work for, Unichem Chemical, this is how we reacted fats and oils, mainly tallow, yellow grease, and white grease. We had special columns we called splitters, because essentially to people who weren't organic chemists when this was being set up, we're splitting this in half, sort of. And this is what we did. And we did that to the tune, like I said, about 2 to 3 million pounds a week, every week of the year. Chemical plants, most of them never shut down at night and never shut down the weekend and never shut down in a holiday. They run all the time. So this is what we did. And let me see if I can real quick. I don't know if I'll be successful. Nope. Let me try one more thing. Bingo. Sort of. We have better one. They used to have a picture of that plant here. All right, everybody see that picture on your screen? That's the splitting column, two of them. We had 5 of them that big that ran. And steam comes in at the top, the fat is injected in the middle, they reach together and they separate, or they put you both at the top, they separate, and the fat and glycerin comes out at the bottom. Split. And it was quite interesting. And it wasn't fun to climb up to the top of the tower in a snowstorm. I'd do that once. It was not fun. Oh no, I'm gone over our time. All right, let's take a break. Come back in 5 minutes. I'll see you at 1:56. I'm gonna get up and stretch. time to get going. If it looks like I'm happy, I am. I just checked my mail and something I was expecting that I ordered came in and I'm happy. There, hold on one sec. You see this? One of my hobbies is RGB LEDs, and I just got 25 of these in from China. Yep, that's the cheapest place to buy it. If you're not familiar with AliExpress, I think it's called. I always think of it as Ali. Hold on, let's find out. Yeah, AliExpress. If you're not familiar with this, it's probably the best place right now to get reasonably priced electronics. They have a lot of other stuff and a lot of it's garbage, but their electronics for my hobbies, wire and capacitors, resistors and everything. Yeah, you got to wait a couple weeks to get here, but the price differential from what you get from Amazon or elsewhere is tremendous. But anyways, that's not why you came to see me. Let's get to work. Now, we were talking about how steam is a way of reacting an ester to make alcohol plus a carboxylic acid. So I would ask you, and I'll help you out. If I had tallow, and this is what we did at that company, and you reacted with steam, what are the three products you get? 1, 2, 3. And as soon as you see tallow, you should have this triglyceride in mind. And when you react it with steam, remember that's hot water. Guess what? I'm going to let you try this all out, all on your own. Am I nice or am I nice? I'm going to share the fun. And if any of you happen to be in Champaign or Champaign-Urbana, don't forget to spread the word that I'll be teaching organic online next semester. Any takers or interested people, Calvin?
Not that I know of yet, but I have
All
told
right.
some people.
Well, unfortunately, I can't give you any kickbacks. Because this organic chemistry one semester at University of Illinois Champaign still as awful as it has been.
Yeah, it stinks.
I bet you never thought you could find out that organic chemistry might be fun. It is, but I'm biased. And thank you for your feedback, Calvin. I better shut up so he can finish. And when you're done, give me a thumbs up. All right, I think everybody's done. So let's take a look at this. Well, tallow is this designation that I'm using for this class. And really, it works quite well in real world situations when you think about that, which is why I'm teaching this to you. And what this really is 3 esters. And as I showed you, steam, which is hot water, you get the alcohol plus the carboxylic acid you would have used to make that ester. And therefore, we have our 3 esters. Ester 1 gives this alcohol plus stearic acid. Ester 2 gives this alcohol plus oleic acid, which for this reaction you can abbreviate. If I ask you to draw the structure of oleic or stearic, then use carbon hydrogens. And finally, ester number 3, you get this alcohol, and notice this part will give you stearic acid. So if you want, you can put a 2 there. You don't really have to, because the 3 products are glycerin, stearic acid, oleic acid. And like I said, we used to do about 2 to 3 million pounds a week of this reaction with tallow, but whenever we could get white grease and yellow grease, we'd use that instead. You get the same products, this is cheaper. Interesting, when we ran this reaction, and I started with this company, one of my jobs was being in charge of quality control. And when you buy tallow, yellow grease, and white grease, you buy any chemical from anybody, you put in what's called specifications. When you go and buy a car, you say like, well, I want this brand, like an Explorer. I want 2 or 4 doors and what color. What you're doing is telling them what specifications you want their car. Well, with tallow, yellow grease, and white grease, there was an interesting specification I'd never heard about. And that's the amount of plastic in there, polyethylene. And what is that? Well, if there's polyethylene plastic and tallow, those splitters you saw, they get clogged and they can blow up because the plastic solidifies in those columns. Where does tallow get plastic? Well, the companies that make the tallow from the actual fat, called renderers, well, they get those from butcher shops and companies that trim and make different slice types, beef packers or meat packers, like in Iowa. And the excess fat, which they sell to renderers, instead of throwing it away, I don't know where they throw it away, all those millions of pounds, they put in gondolas, garbage cans with plastic liners. And the renderers, if they're lazy, don't even bother to take the liners out, and the plastic gets dissolved into fat. And that's why they had it. Now, there was another, it's time for Dr. White to gross you out. There was another spec on tallow, white grease, and yellow grease. And that was, are you ready for this? The percent teeth, hair, and hide in it. And there was a way to measure that. You didn't want that when you were running. We wanted a pure product. By the way, renderers, if you've ever rendered fat, like made chicken fat from the chicken skin, you heat it up. Well, there are companies that do that. And the company I work for, Unichem, bought the chemical division from a renderer, Darling and Company. And that's the one smell you never get used to being near a rendering company. And luckily my office was upwind, so I didn't get to smell it. It was on the same site. But do I have time? Yeah. What do renderers do? They get carcasses and fat from butchers and slaughterhouses. If a cow dies before it's slaughtered, they can't slaughter it and sell it for the meat. Well, what do? They just ship it to a rendering company. Well, one morning, and at this company, they let me start early. I'd get there about 6:30 in the morning. I could leave a little earlier unless I had a meeting to go to, and that way I missed rush hour traffic on the Dan Ryan and the Kennedy to come back out to the suburbs, which was a good thing. Well, anyways, one morning it was winter, it was like 8 or 10 below. And because I was a senior manager, I didn't park in the regular parking lot. I went through the security gate. All chemical companies have security gates with guards, that they knew me. And I had a special place under an overhang, fancy, that the senior managers could park. While I'm driving in the plant, it's like a regular street on a side street. And part of that area was the render. And right in the middle of the plant street, what's there? A dead frozen cow on its back with its legs sticking up. I drove around it and parked, and I went to my office, and the renders plant manager started early too. I called them up because I was in charge of waste treatment for both our company and theirs. I called them up, I forgot his name right now, and said, "You got a problem, what's wrong?" "There's a dead cow in the by the entrance. Someone fell off the truck when you were getting delivery." So, "Oh, sorry about that. We'll send a lift truck out to pick it up." And they did. Interesting way to start your day. Not. All right, let's look at something important. A reaction you did a long time ago. Long time ago, it seems like a long time ago, you learned double bonds, which have one pi bond and one sigma bond. You reacted with hydrogen and catalyst, and the catalyst can be nickel, platinum, or palladium, and you break the pi bond, and each carbon gets a hydrogen. That's you learned for test one. Now let's try something interesting. This is oleic acid. If I add hydrogen and nickel, what do I get? I'm going to let you try that. Now, remember, this is a carboxylic acid, and a carboxylic acid will not react with hydrogen and catalyst. So it's your turn. And when you're done, don't forget, give me a thumbs up. Remember, carboxylic acid will not react with hydrogen and a catalyst. Either will an ester. Anybody need a little help from Dr. White? Give me a wave your hand if you're not sure what to do. All right, let me show you what's different. What's not a carbon-carbon steel? Oh, a double bond. Now, this is a carboxylic acid. That's not going to react. No reaction. But a double bond it is. Do you break carbon-carbon single bonds? No. So what happens is the following. Here's a general reaction. Break the pi bond. Each carbon of the double bond gets a hydrogen. And I'll write the rest of the molecule. And that's what happened here. Now, if you notice, hydrogen here, hydrogen there, this is a CH2. Hydrogen here, hydrogen there, that's the CH2. So if I have 7 CH2s plus 2 more plus 7, 7 plus 7 is 14, plus 2 more is 16, I can rewrite this like that. These are the same molecule, just rewriting it different. And what molecule is this? Stearic acid. And if you hydrogenate oleic acid, you'll get stearic acid. Everybody see that? So with that in mind, I'm going to have you do another reaction. Give the organic product or products for the following. Uh-oh, what do I do? I'll let you think about it for another, I'm looking at my clock, 30 seconds. I'll give you a bonus 10 seconds. And I'll watch down here I'm staring at. Thank you, Megan. All right, time's up. What's this? This is oleic acid. If you hydrogenate it, hydrogen in a catalyst, what did you learn up here? Oleic acid, hydrogen in a catalyst gives you stearic acid, which I can write like this. And what I have here, this reaction, is this reaction up here, where I'm showing you what R sub O and R sub S is. Everybody with me on that? Do you understand what I did? R sub O had a double bond. When you hydrogenate it, you get R sub S, which this part is R sub O. This part is R sub S. So with that in mind, let's look at the following. Now, if you have a highly unsaturated oil, like vegetable oil, think of it, this structure. Most of the R groups are oleal. You'll have a little linoleic and linolenic, but not enough. And the question would be, and probably you need excess, but I'd rarely put that there. because organic chemists are lazy, what would be the product of that compound? And esters do not react with hydrogen in a catalyst. And when you're done, give me a thumbs up. Remember, hint, thank you, Megan. All right, I think everybody's done. So let's look at this. Well, I have an ester here, and that won't react with a reaction conditions of hydrogen gas and a catalyst, nickel. But in R sub O, I have a double bond. And what did you learn up here? R sub O becomes R sub S, the sterile group like that. So what really happens here, remember, the ester does not react. So I'm not going to react it. But the R group becomes R sub S. And that's the change. And what that means is you've lost the double bond that was in R sub O. Now, I think I have a slide for that. First, I'll let everybody write this down. And when you're done, if you're writing it down, give me a thumbs up. All right, I think everybody's done. So let's go to the slides. Already did saponification. And that's hydrogenation of a fat or oil with hydrogen gas and a catalyst, which we just did. Now, why would somebody want to do this? Good question. Well, this is a liquid. Think of corn oil, vegetable oil. When you hydrogenate a fat or oil, you'll get a solid or semi-solid. All right, so what? Well, this stuff is inexpensive, cheap. If I hydrogenate it, which is not an expensive reaction, and I get this hydrogenated fats and oils, and I put a little water in there, some yellow coloring and some flavoring, I make margarine. And I can charge a lot of money for that compared to what I have here. And that way I can make a lot of money. And companies do that. Now, how many of you have ever heard hydrogenated fats and oils are bad for you? They clog up your arteries. Yep, my heart's on this side. Well, guess what? The companies that make margarine don't care. They've improved a little. Now, when I worked at Unichem Chemical, being a senior manager, once a year, they had a nice thing for all the senior managers, research, marketing, sales, everywhere, where we would meet at this beautiful resort in upper state New York. I don't know if it was the Catskills or not. And they had these chalets where you had these huge bedroom, almost like little suites. They're really sweet. Each manager had one. There were 4 suites to the chalet. They had a lot of chalets because we'd have a couple hundred people. And one year I went there also. Science, chemistry company, chemical companies know how to party hard. We meet from 9 to 5, have dinner, and then they'd pay for it, the company. We'd party hard. But anyways, don't say anything about that. A lot of stories I could tell you about that. But anyways, this one time I was up there were about 150, 200 of us in this opening session. We were in the ballroom, the main room of this resort. And a couple people were giving talks. About every 10 minutes, the owner of the resort would come in and say, so-and-so here, I have an urgent call for you. This was before cell phones. Wow, that was a while ago, but it was. And this was the late 1980s. Wow, that's a long time ago, over 30 years. Anyways, he'd go, come back, and 10 minutes later, the guy would come in looking for him again. He'd go. After about 5 times, the senior vice president in charge of that whole meeting called them and called them up and said, come here, why don't you just go back to your office? Whatever the problem is, you're needed there. And he did. I found out later through some other people what was the problem. This was the marketing sales manager in charge of a new product. I was working for the company Unichem, which was this meeting was for Unilever. And he was in charge of their new product coming out in the whole United States in a couple of weeks. I can't believe it's butter, or margarine, whatever the name is. And the problem was they made like about 500,000 units, tubs. And somebody went after they'd made it and they were in storage before they shipped out, open a box, open the top, and the metal foil was puffed up. Open some more and they're puffed up. So they had to solve it, and they did. But that guy had an awful time until they did. And luckily the rollout went well and everything else. But now you know, why do you make hydrogenated fats and oils? Because you can put them in products you can sell as a artificial butter, which unfortunately is bad for you, but the companies that do that make a lot of money. Oh, I just thought of something. I didn't teach you something. This will not be on a test. Do I have time? The reason I thought of that, this is called acetyl acetone. And this is the chemical they're using a slightly different one now, that gave microwave popcorn that butter taste. And the reason I thought of that was because I also use hydrogenated fats and oils to help also give that butter taste, and microwave popcorn that's buttered. I don't buy that. Haven't for decades. I use microwave where I buy my own, and then I put it in a microwave popper and I can control what's put on there. Well, this was the chemical that gave that the taste. Well, it turned out the workers that were making those products started coming down with a very deadly lung disease, to the point where it was called popcorn makers' lung disease. Or popcorn maker's lung. And here it's diacetyl, and it's that ketone or diketone I was showing you. And that gave it its buttery flavor and smell, which people like on their popcorn. When I was younger, I loved buttered popcorn. I stay away from it now. And eventually they changed it, another chemical, so it wouldn't get these people sick. Now, the reason I'm telling you the story is there's one shady lawyer, and I'm talking about shady lawyers. I know some very good lawyers, so I like them. But this guy, and it made the news, he sued the company claiming he had popcorn lung disease. Why? Because he would eat about 7 or 8 bags of popcorn a day. He claimed it got thrown out, but it's just interesting chemicals, and they can have good and bad things. All right. Guess what time it is? It's time for today's lab. And today's lab, I really wish you were in face-to-face, is a fun lab. And it deals with making esters. And let me close something. Let me open something else. If we were in a lab, I'd be handing it out to you right now. Actually, I'd hand it out Monday. But anyways, I posted it Monday. Everybody see the carboxylate anion esters lab on there? And let's talk about esters. Esters are responsible for the many fruits and flower odors, and also taste from fruits and flowers, mainly fruits, and also some vegetables. Also, carboxylate anions are interesting molecules found in different things. And depending on the chain length, they can be very water soluble. They can also hydrogen bond. Now, the first part and second part, you're going to be working with this reaction. If you take a carboxylic acid and an alcohol, you make an ester. And what you'll do, if you were face-to-face, you'd be making esters. Now, in the first one, part A, you're going to make 2 different esters. Oh, by the way, it's totally permitted to laugh hard at my artwork. You're going to have 2 large test tubes. In each test tube, you'll put 1 milliliter of glacial acetic acid. Now, glacial means 100% pure, and that's the carboxylic acid. Now, in one test tube, you'll put ethanol. In the other test tube, you'll put the alcohol 3-methyl-1-butanol, also known as isoamyl alcohol. You'll tap them, mix the test tube, and then carefully in a hood in each test tube A and B, you will place 1 milliliter drop-wise of sulfuric acid, concentrated sulfuric acid, a dangerous chemical, but that's your H+. And then you'll put it in a beaker of water that's at 50 degrees C. I teach you how to do that. And heat it for about 10 minutes. And you'll have afterward beaker A and beaker B. And in beaker with some ice in it, about 1/3 of it is ice, and they're small beakers. And beaker A you'll pour test tube A in. In beaker B, you'll pour test tube B in. And what you'll do afterward is cautiously take it out the hood, put it near your face, and go like this to smell it. Everybody see what I'm doing? And you'll write down what you would smell. Unfortunately, we're not in the lab, so I gave you the data. And for that, I'm asking you here in table 1, part A, draw the ester where you react acetic acid with ethanol and acetic acid with isoamyl alcohol. And if you were there, it would smell like nail polish remover for the first one, and you would smell banana and be really surprised for the second one. Now, if you happen to be in a supermarket or if you have it at home, next time you have a chance, smell a banana. And it's the ester you're making here. And if you have a nail polish remover, it's this ester. Now, in part B, you'll use salicylic acid, same thing in a test tube. You'll add some methanol, add the acid, and heat it. And you heat it a little longer, and then you'll put it in the beaker with the ice, and you'll smell it. And it will smell like mint or minty lifesavers. And that's the ester they use. How many of you have ever heard of contains artificial flavors? I think you've seen that on labels. Guess where they make it? Instead of putting mint in there or banana, like in Taffy Laffy, I think it was Taffy, what is it, Taffy something banana? They use those esters they make in a chemical plant. Purify them though heavily so you don't get sick. And in part C, the last one, you'll do the same thing. Here again, you'll put glacial acetic acid. Glacial is the word meaning pure acetic acid. And then you'll add 1.5 milliliters of 1-octanol, the alcohol. You'll mix it, then add the sulfuric acid, heat it longer, and pour it into a beaker and smell it. And it has this fruity smell, that ester. And this is one of the key esters in oranges. Like I said, unfortunately, you're not going to be able to smell it, but next time you're in a supermarket or if you have some at home, pick up an orange and smell it. What you're smelling is the ester formed from acetic acid and 1-octanol. Now, in this one, this is something interesting. And if I was at ECC, I'd hold up one, but I don't. So let's go out to the internet and see if I can find one real quick. All right, everybody see on the screen different types of diapers. These are super absorbent diapers, like this one right here. And if you were to look at that, let me, super absorbent, and they're extremely thin, not super thick. How do they do that? Organic chemistry. And that's this part. There's a polymer called superabsorbent polymer, or SAP. It's really polysodium acrylate. Now, poly means many. Sodium acrylate is it's made from acrylic acid and has this structure. This whole thing, including that, is repeated over and over again, and N is about 1 million. It's big. It's a polymer. Now, carboxylate anions hydrogen bond better than carboxylic acids. So this will absorb water, bond to it better than this, even though it will hydrogen bond. Now, in this part of the lab, I actually have, we used to at one time cut up diapers. I'd be holding up a diaper and opening it up and show you the polysodium acrylate that's in the fiber of the diaper to make it a super absorbent and thin, but I don't have any at home. No, I don't use them, thank God. Anyways, I don't have any kids around any here who use them. So we use the actual chemical, which is a white powder. And this part, you're going to find out, was I lying to you about this or not? You never know, I could be. And what you're going to do is start out with sodium polyacid, that should be acrylate.
Dr. White,
Yep.
are you writing on the lab right now? Because we still see the
I forgot to
full screen.
change. Thank you, Calvin. I just wanted, now do you see it?
Yes.
All right, let's go back. I apologize. Do you see that on top now? Let's instant replay, and it's not even summer. All right, here's the sodium acrylate right here. Is CH2CH, then the carbonyl carboxylate anion, all inside that bracket, and there are N of them. N is about 1 million. Now, up here, just in general, this is a carboxylate anion. Thank you again, Calvin. And it hydrogen bonds better than a carboxylic acid. In today's lab, you're going to find out, am I lying to you or not? I'm not, but you'd find out in the lab. And what you're going to do, and I just realized this should be not acetate, this should be acrylate. And what you're going to do is first take some and put it in a beaker and weigh it out. And then you'll add some water. In a second, you'll add both 2 beakers, 1/10 of a gram in 2 beakers. Now to beaker 1, you'll add, or both beakers, you'll add 5 milliliters deionized water and stir, and you'll observe. Now the second beaker, you'll add 10 drops of hydrochloric acid till the pH is less than 5, meaning it's acidic. And then you'll observe it. Then that same beaker, you'll now add drop-wise, about 10, 20 drops of 1 molar sodium hydroxide, a base. And then you'll observe what's happening. And let me just show you, think about this. In general, if I have a carboxylate anion and I add H+ in water, I'll get back the carboxylic acid. And then if I have the carboxylic acid and I add base and water, remember this is acidic proton, I'll get back my carboxylic acid. And for this reaction, what you're going to do is start out here. This is your acrylate. You'll add acid. You'll make polyacrylic acid, it's called. And then you'll add more base and get back your acrylate, sodium acrylate. Does that make a difference? Well, the first speaker was just the water and the sodium polyacrylate. and it becomes a gel. That's how it absorbs moisture in a diaper. By the way, urine is mostly water, if you weren't familiar with that. And that's what this absorbs. Now, the second beaker, you have the water, you get this gel. Now you're going to add HCl. Ooh, it becomes a liquid. I wonder what's not hydrogen bonding. And then you'll add base again, and it becomes a gel. I wonder what's now hydrogen bonding. And that's today's lab. And here are the questions. And with that, I'm done for today. Thank you for coming today to my class. For those of you who came late, stick around for about 3 minutes after I do my official log off, because I want to say something that you missed if you came in late, and I'll be cutting it out of the video like the beginning. But anyways, don't forget, if you need help, I have my office hour tonight from 5 to 6:15. I'm going to say goodbye, but those who came in late, stick a couple minutes afterward. With that, gehen gesund, be healthy. Bye now.